Boom. Hello and welcome back to Calculus 2, section 9.3, Taylor series. This is take 2. So the first time we did this, the network exploded. So let's see if it works now. So we start with the definition of Taylor series, which you've seen before in previous 2 sections. And we know that minus a, right? The a, again. Start normally, come on. So when we have a is centered at a, and we've seen with the radius of convergence and interval of convergence that at a is always in the center, and then radius goes both sides, and the interval of convergence is twice the radius. Could be infinite, could be at one point, and so on. Now, we can expand this formula when we calculate everything at 0. Zeroth derivative of a function is the function itself. So we have f of a plus f prime of a x minus a plus f double prime of a over 2 x minus a squared plus f, the third derivative of f computed at a over 3 factorial, which is 6 times x minus a cubed plus dot 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 going to infinity. Now, the Taylor expansion of a function is equal to the function if you use all infinity of the terms. But what we've seen in our lectures 1 and 2 is that if we use, 3 to 4 terms, we are already having tens of thousands of precision. So we don't have to worry about dragging too many terms in Taylor series. They converge quickly to a function. Now, if you want the exact answer, you have to use all infinity of the terms. But we're seeing that it's sufficient to use, 3 or 4. And on your exam, you will expect of me to ask you to find a Taylor series for a function. And I will ask for 3 terms, maybe 4 terms. If you have 4 terms, you are clearly calculating 3 derivatives, right? Because the first term, as you can see, is function itself. So power series, so Taylor series is a power series, and what we have here as example, we've seen earlier that e to the x is equal to the summation 0 to infinity of x to the n divided by n factorial, which is further equal to 1 plus x squared over 2 plus x cubed over 6 plus dot 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 going forever. We also seen the power series for, say, cosine x, which was the power series which had the alternating term -1 to the n, and then we had x to the 2n divided by 2n factorial. Now this one was 1 minus x squared over 2 plus x to the 4 over 24 minus x to the 6 over 720 plus dot 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 going forever. This 720 is the 6 factorial. 5 factorial is 120 times 6 is 720 for 6 factorial. So this is supposed to say e to the x disappeared. So we have function e to the x, we have function cosine x. You can figure this out for ln and all of different functions that you might want to use it for. So Taylor series are very, very, very useful. Now, when I say that we are approximating functions using Taylor series, we need to be careful about shifting the functions to the right place where we need to do the expansion. So, remember that when you had y equals x squared, it was a parabola that went through 0, 0. And when you had y equal x minus 2 squared, was a parabola that went through 2. So this part of minus 2 in parentheses was a shift right. We do the same thing with power series with this x minus a. We shift the power series to left or right, depending on value, or whether a is positive or negative. So we shift that power series left to right to actually match it better with the function that we are approximating. So it is important to know how to deal with that a. So we will say, and here is the example, we will say use Taylor series to expand y equal e to the x. Let's do e to the 3x around x equals, let's say, 5. Now this 5 is the a. Now I said x equals 5 rather than a equals 5 because this is x equals a. A is that number on x-axis, so that's why it's x equal to that we are going to expand. So how do we do this? Let's say give 4 terms. Give 4 terms. So what do? Well, we know that we need derivatives. So we are going to say that y, which is, you can call it f of x if you want, is e to the 3x. Then f prime is 3e to the 3x. Then f double prime is 9e to the 3x. And f triple prime, you can also use the parenthesis notation, is 27e to the 3x. So these are the 3 derivatives. We know if we want 4 terms, right? You have the function plus, I mean, you can see it here, right? 1, 2, 3, 4. You stop when the number of rows you have equals the amount of terms you need. So now, the formula says that you are supposed to take f of a plus f prime of a divided by 1, x minus a to the first power, plus the second derivative a divided by 2 factorial, which is 2, x minus a squared, plus the third derivative computed at a divided by 6, x minus a cubed. Now this is now approximation because we are using finite amount of terms, just 4. So what is the e to the 3x approximately equal to? It's approximately equal to, we are expanding around 5, so it's approximately equal to f of 5 plus f prime of 5 times x minus 5 plus f double prime of 5 divided by 2 x minus 5 squared plus f triple prime computed at 5 divided by 6 x minus 5 cubed. Now you see that this is going to be one really annoying calculation, right, from this point on, because you have to expand all of this. You have x minus 5 cubed. I know. Awesome, right? So f to the 5 is e to 15. That's all it is, right? Because you plug 5 for a, which is x, plus the derivative. So that's going to be 3e to 15 times x minus 5. And then we have plus 9e to 15 divided by 2, x minus 5 squared, plus 27e to 15 over 6, x minus 5 cubed. Now we are simplifying. Well, each one of these has e to 15. We're not going to compute that and give decimals, so we're just going to factor e to the 15. The first term gives us 1 plus, and now we are left with 3x minus 15 as I distribute the 3, right? I factor out e to 15 and I distribute 3 inside, so that's what I have. Now e to the 15 goes outside. I have 9 halves that survived, and I have to expand FOIL x minus 5. So this is going to be plus 9 halves x squared minus, that's going to be 10x, so 45x, and then minus plus 25, so 9 times 25 over 2, whatever. Plus 27 and 6 canceled by 3, so you have 9 halves again. So 9 halves, e to the 15 is out, and you have the expansion of the cube now, and expansion of the cube inside is going to be x to the 3 minus 15x squared plus 15x, and then finally minus 125. 9 times 25, I didn't compute. So now if you carefully look into this, right, you can pull some common terms. Well, first of all, you have 1 minus 15, so that's for now 3x minus 14. That's easy. Now I should have left this as 9 times 10 over 2. It's better. So now look what I have. Plus, you can factor out 9 halves, and you're left with x cubed. And now you have, when you factor out 9 halves, you have 1x squared minus this one is minus 14x squared. When you factor out 9 halves, you're left with negative 10 plus, so plus 5x. And when you factor out 9, it's 25 minus 125 minus 100. That's if you factor out 9 halves in front. So this is, you know, just manipulation. What happened? Yeah, it's 9 times 10 over 2. Yeah, but I want to factor out. I want to factor out 9 halves everywhere. So I take these 4 9/2 and I factor them here. So each term has 9/2 in front, and I factor all those 9/2. So then you have x cubed has nothing to combine with, so x cubed gets copied. You have positive, so all the 9/2 are out. You have 1x squared positive, so minus 14 plus 1 is negative 14. 9/2 is out, you have negative 10x and positive 15x, so that's positive 5x. 9/2 is out, you have 25 and 125, minus 125 and plus 25 is negative 100. You'll see that now, by simply distributing 9/2 everywhere, you can add 3x to this term when you add 9/2, and you have negative 14 to this term here, which would be 50 times 9, 450. And you will have a polynomial times a constant e to 15. It's a polynomial. With that polynomial, integrating, differentiating, everything easy, going quick. So Taylor series turn everything into a polynomial, and you see that calculations for this tend to be lengthy. We have to agree, this is extremely easy and simple, but it's really, really, really tiresome in terms of calculations. A lot of calculations, a lot of opportunities to make mistakes. In the textbook, they computed Taylor series for cosine x, and they computed for 1 over 1 minus x. So those are given in the textbook. Now we have a special name for the special case. Maclaurin series is a Taylor series centered at 0. That's all it is. So you're not learning new formula, you're not learning new concept. It's just a name. So you can center your Taylor series at any point between negative infinity and positive infinity. If it's centered at 0, it has a special name. Just like you have a special name for log base c. What's the special name for log base c? ln, right? If you have log base c of x, you call that ln x. Special name, this base c could be anything else. You don't have a special name for log 2 of x. You don't, right? But you do have a special name for log base e of x, which is ln x. So the same thing now applies to Maclaurin series. It's nothing new, nothing special. It is that this, when it's centered at 0, we call it this special name, this because obviously he developed that before Taylor did the general case, right? So, where is the homework example? So, compute first 4 terms of Maclaurin series for the function given by f of x. And here's your problem number 12. Ln of 1 plus 4x. There we go. You know what Maclaurin series means. Centered at 0. So every A in a Taylor series becomes 0. And that's Maclaurin series. So you're not going to have x minus A, because A is 0. You're just going to have x. The first, x squared, x cubed. So no polynomial extensions, right? It's going to be much faster, much easier. I'm going to start working on this, but you work it out on your spots. I'm sorry? So? It's good? Right, so now we have f of 0, that's going to be ln 1, plus the derivative computed at 0 is 4 divided by 1, so it's just a 4, times x, plus the next derivative computed at 0 is negative 16, needs to be cut in half, x squared, and the next derivative is 64, needs to be divided by 6 because it's 3 factorial, and then x cubed. So now to simplify this, ln of 1 plus 4x is, oh, this is 0. Yeah. Alright, 0 plus 4x minus 8x squared plus, and now we divide, we cancel here at 32 over 3 x cubed. I asked for 4 terms, the first term disappeared. So we take one more derivative. Yeah, such is life. So what's the 64 times, that's 240, 256. So the new term we are adding is going to be negative 256 divided by 24, x to the 4. So that's a new term. So now our ln of 1 plus 4x is 4x minus 8x squared plus 32 over 3x cubed, and then we have to simplify here. So 256 is base 2, 2, 4, 8, 16, 32, 64, 128, 256, so 2 to the 8 divided by, and 24 can be written as 8 times 3, so 2 cubed times 3. So this will cancel, leaving you 2 to the 5, and 2 to the 5 is 32, so negative 32 over 3 x to the 4th. And there's the 4 terms. I will. Give me a second. So why? You might go, why? Well, first off, to integrate this, you have to use the u sub and then integration by parts. To integrate that, you need to use about 17 points of IQ. Fair? the calculation of a number. You have to be very careful. Can I use this polynomial to compute 7?
No.
Why not? Because it's centered at 0 and 7 is far away. I can use this polynomial here to calculate 0.2, 0.73, all right? I cannot use this to compute 7, all right? Because it's centered at 0. If you want to use this to compute 7, expand it at 7. If you have to compute 15.2, expand it at 15. You have to do the expansion around calculation that you have to find. Otherwise, you will find that your answer and the actual answer are really off by a lot.
When you say expand,
What happened?
when you say expand,
Start the whole problem from scratch and expand it around the point of interest. So if I'm asking you to compute 2.3, you will actually do the Taylor expansion at 2, which was the previous problem with all of those things. This one was Maclaurin. Maclaurin is always centered around 0, so you are going to only compute values like negative, negative 0.3, 1/2. Okay, also to compute with that polynomial, right? But not too much. Don't venture far. For this. Okay, guys, so the question is, what are we doing with this later? Later, for those of you in mathematics, you're going to run into whole graduate courses called Asymptotics 1 and Asymptotics 2, where all you learn are these power series for very complex calculations, for nonlinear equations, nonlinear differential systems, and all that kind of stuff. What you do is you take one power series, you embed that into another power series, look for critical points, you look for all these awesome things. So right now what we are doing is we are learning the very basic one. And that one that we have is not nested. Imagine now that this is a function composition here of ln of sine of something. So each sine is this x, sine, and each one of those is the Taylor series, -1 to the n. So you have the Taylor series within the Taylor series nested. And you can keep nesting it like that. So nested within the, right? Or go find the first 10 terms there. It's a calculation. It takes 3 years to compute. So this is going to really pile up in a grad math course if you want to go and explore. Here, I'm going to ask you for first 4 terms. If the first term dies like it died here, oh my goodness, you have to calculate another derivative, and I don't know, somehow you'll manage, right? What are the evil ones? Well, obviously sine and cosine are evil ones because every other term is gone. So if you're looking for the first 4 terms of sine, you have to calculate 8 terms because every other term dies. That should be common sense. But that's very rare. You might lose the first term sometimes. It happened here. This was problem 12. So you might lose the first term. Generally, you don't. Generally, they all stick around. And then the sine and cosine lose every other one. So if I say first 5 terms of sine and cosine, 10 terms, right? And every other one will drop because sine of 0 is 0 every time, right? So all of those terms drop. Yes, sir?
I was just saying before, I think, isn't it supposed to be 64 x cubed instead of...
Well, fine, I'll put 64. Is it 64?
Well, because I don't think you times it by 2 when you took the derivative to begin with.
Times by 2?
Right, but you had, or maybe I just can't do change over, right? You only times by 4 the inside, the outside. You only times by -1. Should it be -2 or just I just not change over?
Oh yeah, there will be a negative 2.
So we double it. Which stat changes your mind?
Okay, so this is 64, you're right.
Yeah.
Okay, that's a 64, and then the last one also changes.
Yeah.
So wait, 64. So this is not 16, this is 32 over here. No, this is 16.
Yeah.
This is 32. Wait, what was this? It's supposed to be 128, right?
Yes, 128.
And then this term is not 256. It's what? So it's times 128 times 12. That's what it is. 128 times 12.
1,536.
1,000.
536.
And we divide that by 24
It's 64.
over 3, right?
It would just be 64.
Great. All right, problem fixed. Thank you. Another one? Of course, you love this stuff.
That's power.
Especially the power series. Next problem is your favorite problem. 20. Give first 3 terms. A chlorine again. What happened with my eye? With the function f of x equals to sine hyperbolic of 2x. What happened? All of them. Maybe, I don't know. I asked for the first three terms. I can achieve that with two derivatives, plus the original function. I don't know. Is it? It's a hyperbolic. I know. 6.2, 6.10. Our course. Zero? You can't center it at 2x. You can center it at 2, but it's a Maclaurin series, so you're centering it at 0.
I didn't still need the spring starting. I thought it was into 3x.
Yeah, starting function is the original function that it's given.
Yeah, we were using.
Oh, you did something.
I was using center.
So cosine hyperbolic of 0 is 1. So we have 0 plus 2x plus 0. Oops. Plus 4/3 x cubed two terms drop. You have to add 2 more because the next one's going to be 0. Yeah, sines, cosines, and hyperbolics do the same thing. They drop every other.
4 more.
They don't do negative.
We're going to need 4 more.
Hyperbolic sign in terms of e from 610 and then 1960. All right. We're going to jump over the binomial series and we're going to mention the remainder. Again, this is not an honors section, so we're not going to, go crazy. So, what is the remainder? So what's the remainder? The remainder is just the next term. The first one you throw away. So, if you say that f of x is approximated by, and you go and say summation 0 to, observe that I'm using a finite value, let's say k, of f of the nth derivative of a divided by divided by n factorial x to the x minus a to the n. I'm not going to infinity. I'm going to k equals, come on in, it's Calculus 2. It's good. So I'm not going all the way to infinity with this one. You see the k on top of the sum, right? Which is the reason why I put the squiggly equal sign, which means approximation. Fair? So I'm going to go to a k and approximate the function. Now, what's the remainder? The error. Remainder is going to be the next term. So the n plus 1 derivative computed at a, n plus 1 factorial x minus a to the n plus 1. Now this is a single term. There are infinitely many terms after this term, But most of the error that we make by dropping all of the infinity of the terms will be concentrated in the first term you drop. So most of the error will be concentrated there. So we just look at the first term we throw away. So if I ask you, what is the approximate error for the, for the first three terms, approximating something, what do you need to compute? Just the fourth term. That's all it is. So if I'm asking for the three terms, the error is concentrated in the fourth term. If I ask you for the first four terms, the error is concentrated in the fifth term. You just compute the value of that term, right? That's all it is. So you will compute the value of the, let's say it's a fourth term. You have derivatives, compute A, have the exponent, and you compute that term. So that covers the story on Taylor series. That's 9.3. And now we have extremely short section 9.4, working with power series or Taylor series, whatever they it's synonymous for this class. Yeah, working with Taylor series. So in this section 9.4, I will restart the stream. In this section, we have two steps. Step number one, take the function and turn it into a power series. And then step number two, well, you integrate or differentiate, whatever needs to be done. Over and out. Now, I'm not going, obviously, to waste your time there differentiating and integrating polynomials. You know how to do that. You also know how. So it's a waste of section. If you go to other textbooks, this is just a footnote example of something, because clearly, right, you are turning these functions that you cannot integrate, or it's really tough to integrate, into a polynomial and dealing with it like that. So let's restart the stream and spend 5 minutes there.